Hello and welcome to the demo video for the IndoorView project. This is a capstone design project with the Systems and Computer Engineering Department at Carleton University, and the project was supervised by Dr. Mohammed Atia. So the IndoorView is a system-level project that aims to create an interactive panoramic viewing system for indoor spaces, similar to Google Street View. It was also designed to augment or extend Carleton's current campus map, which is limited to building-level maps. My name is Dare, and I will start by demoing the data collection software and process. Then Emad will talk about the image capture. Then Gregory will show the image control or transfer mechanism. And then after that, Ananya will demo our image filtering feature. And then finally, Zoya will put it all together with the user-facing web application. Please enjoy our video. Right, so the first step is to launch the IndoorView program. And then we're going to create a map and give it a name. We'll just call it demo for now. And this is going to bring up the RViz interface where you can see the map is already being created. And this is using the SLAM algorithm to create the map. So as we start moving the robot, the map keeps getting updated as it encounters new territory. And after the user has created the map, the next thing is to click on points on the map where the photos will be captured in order. So we're just going to do 2 points for now. And then after that's done, you go back into the program and then save the map. So we use the save the map command, and once this is complete, the points are going to be saved to the database, as you can see, and then the map creation phase is complete. And then we go attach the camera to the robot. As you can see here, after the camera has been attached, this is what it looks like. Next, we need to localize the robot before we start navigation. So once we perform the localization, it's going to take a LiDAR scan of its immediate surroundings, so a quick LiDAR scan, and then try to match that to the map that we captured in the previous phase. And if I'm doing that in the localization software, I can just show you here. You have the template, and then we have the actual map, and it shows the detected point where the best match was encountered. So going back to our process now, we can see that here we're still capturing our template scan. And then once that is done, it's going to save it, perform the localization, and then put in the results into RViz, which is going to be our navigation software. So here you can see the robot move to this new position where it determined that was the best position. And then we can perform navigation, and the robot's just going to move from its current location to the first point. Then it's going to stop and then capture a photo. And then Gregory and Emad are going to talk more about this image capture process in later parts of this video. Then we go on to the second point. And then when we get to the second point, we do the same thing. We stop and capture a video. We capture a photo. And once that's done, the data collection process is pretty much complete. But next, I'm just going to show you what the database looks like. So if we go into our database, we have a maps table, and you can see the demo maps is added. And then if we go into the table for the demo itself, we can see information for the 2 points. So the coordinates of the points, and then the location of the images in the server. And that concludes the data collection process.
When the robot is fully functional and is able to navigate, the next component of the IndoorView project is the image capturing system. So here the robot is moving, and when it needs to capture an image, it stops. When it stops to capture an image, the only physical indication of the image capturing system is a small blue light indication on the camera which flickers. This will flicker to indicate that an image was captured. This can be seen in this clip, and other than this, everything else is done autonomously in the background on the Raspberry Pi, which is located on the robot, so it will not be seen at all by the users. However, for the sake of the demonstration, I will go through what happens in the background briefly. Overall, the purpose of the system is to capture images, download those images onto the Raspberry Pi, and then finally reorganize those images as needed by the image transfer system, the database, and the front end. How this works is the first thing it does is kill the gPhoto process, and this process is created every time the camera is connected to the Raspberry Pi or the camera is turned on. And this can be seen here. So it can be seen that the highlighted process is the gphoto 2 process, and that process has a number, and that number is dynamic, that always changes. Now the first thing that happens is the script kills that process automatically without any input from the user. After this, the camera's RAM is cleared, and then a folder is created, and this folder will contain the captured images. Then an image capture command is triggered, and those images are downloaded to that saved folder. And lastly, the camera's RAM is cleared again. To show this process, the image capture Python script is run. So if we check that process again, we can see that it's not there anymore and that it has been deleted. We can also see that a folder was made, a folder named IndoorView images, and if we open that folder, we can see a sample image captured. After this is complete, another script resizes those images as needed by the front end, and then sorts the images by capture type, and then finally it renames them as needed by the database and the image transferring system. So here in the IndoorView images folder, we can see some sample captured images. These images are captured at a size of 5376 pixels by 2688 pixels. When the image rename Python script is ran manually, which in practice is run automatically, it can be seen that the images have been resized. They've been resized to a width of 4096 pixels and a height of 2048 pixels. And finally, the images are sorted and renamed as needed. And this can be seen as follows. This completes the brief overview of the image capturing system, and now these images are ready to be transferred to the remote PC.
So the next part of the project that I will demo is the image capture control and image transfer system. This system was designed to autonomously and remotely control the onboard panoramic camera. This system also transfers the images from the Raspberry Pi to the remote computer. I'll first start off by showing an example of how the capture control system works. In this example, the robot will navigate to 3 points and capture images at those points. This diagram simply represents an overview of the sequence of events that occurs. The first step is to start up the message server on the Raspberry Pi, so it can begin to wait to receive messages and respond appropriately to requested commands. I will now show a demo of the terminal output on the Raspberry Pi. As you can see, the terminal shows the message server being started up on the Raspberry Pi. The server is now waiting to receive messages. At this point, the robot will begin to move in the indoor environment until it reaches a specified point on the map. When this point is reached, the robot stops moving and an image will be captured. To capture an image, the remote computer will send a capture message to the Raspberry Pi computer on the platform. As you can see, the Raspberry Pi has now received this message. The onboard messaging server application will detect this message and execute the capture script. Since there were no more subsequent messages that were received, the server closed that ongoing TCP connection. The robot then continues to move on to the next point, and this capture process is repeated. So as you can see, the robot is now moving to the second point. The robot will stop once again, and the image will be captured. The terminal on the Raspberry Pi now shows the second capture command that was sent. The same process was then repeated for the next point. At this point, you can see the robot navigating to the next point to capture the next image. Once this point was reached, the robot stopped and the image capture command was again sent from the remote computer, as you can see in the terminal window. Now that all the images have been captured, I will now demonstrate what occurs when the images are transferred. Once the robot has arrived at all the points and has captured all the images will be transferred wirelessly from the Raspberry Pi to the remote computer. As you can see in this diagram, the Save All Images command is sent to the Raspberry Pi. The number of images are then counted and the number is sent to the remote computer. The remote computer now knows that it should expect a total of 3 images to arrive. A new TCP connection is then started to transfer things like the image size of the images and the actual image data. A demo of this system in action will now be shown. The lower terminal represents the remote computer and the upper terminal represents the Raspberry Pi. This is a real-time demo that shows what occurs on the output screen of the terminals on both computers. You will now see the two computers communicating back and forth, showing which image is being transferred, and you can also see the size of the images represented in bytes.
In the next section, I will be talking about image filtration algorithm for maps. Map images are created using SLAM algorithm, and that is simultaneous localization and mapping. And these SLAM maps contains large amount of unwanted electronic noise. To reduce this noise, median filter was implemented using Python as the desired programming language. Median filter is a non-linear filter used for signal processing and smoothing while preserving the edges. Median filter is implemented inside the function called ImageFilter that have two parameters: the data, which divides the image pixels in a 2D array, and filter size that will decide the intensity of the filtration. Now I will be running an example on SLAM map for 4th year project room. After running the program, we get two figures, and as you can see, the figure 1 is the original map image and it contains a lot of unwanted noise. And figure 2 is the filtered map, and it's much smoother and contains no or less amount of noise. Now I will be running another example for Mackenzie 4th floor, and as you can see, again the figure 1 is the original map image with noise, and figure 2 is the filtered map image. And for our project, we will be using these filtered map images for our web application.
The next part of the project that we're going to demo is the graphical user interface. A web application was created to display the project to users. This here is the home page and the first page that comes up when users type in the URL. As can be seen here, the first thing that's displayed is the title of the project as well as a small description of the project. These buttons refer to the different map pages available. When users click on these buttons, it brings them to the map page. The map pages are also accessible using the menu bar, as well as the different information pages. Originally, we were planning on obtaining multiple floor maps to demo. However, unfortunately, due to COVID-19 and the implications it brought, we were unable to do so. I'm going to demo a partial map obtained of Mackenzie's 4th floor. This map page is accessible either by clicking on this button or by using the menu bar. So this here is the map page. It provides information to users about how to use the map page. This here is the IndoorView logo. This is the image map with reference areas. These reference areas depict where the panoramic images are available. And this here is the panoramic image display box. Over here is the control bar, and users are able to view the functionality of the control bar by clicking on this button. A pop-up model comes up with the functionality of each of the controls in the control bar listed. This here is the first panoramic image. for the first reference area. So users are able to use the control bar to enter full screen mode. They are also able to zoom out of the panoramic image, as well as zoom in. If users prefer using the control bar than manually moving within the panoramic image, they can use the control bar to navigate right within the image and left. The forward button is used to allow users to move forward within the image map to the next reference area's panoramic image. And the previous arrow is used to allow users to move backwards within the image map to the previous reference area's panoramic image. So by clicking on this reference area on the image map, the respective panoramic image is displayed. Now by using the control bar to move to the next image, the panoramic image that corresponds to this reference area here is then displayed. And moving forward again, moving to the next one, now the panoramic image corresponding to the next reference area is displayed. Users can of course also manually click on the image map to move to the different panoramic image. Now we're at the last panoramic image. So if a user wants to use the control bar to move to the next image, it will wrap back around and bring users back to the first reference area, as can be seen here. This concludes the demo of the map page. I will now show the information pages also available within the web application. So the next page is the applications page. This applications page provides users with information on the different ways IndoorView can be applied. One of the biggest applications of IndoorView is that it contains an indoor functionality that Carleton University's current campus map tool does not possess. Users are able to click on this hyperlink to go to the Carleton University's campus map tool if they'd like to view it and compare it with IndoorView. And there's also just information about the other ways it's applied. Another information page is the About Us page. The About Us page provides users with information about all the team members involved in implementing IndoorView and their respective parts within the project. That concludes the demo on the graphical user interface. Thank you very much for listening.